I do want to talk about how a modern chess playing AI works and how you would go a little beyond your assignment. So in this assignment, if you implement alpha-beta pruning and it works, great, good enough for this assignment. What would you do if you really wanted to make this a good, hardcore, state-of-the-art chess playing system? Well, yeah, it would have to really do chess too, because people would not be happy if your chess playing AI couldn't play chess. Yeah, that's a good point. Openings are well established because there are only a few good ways to start a chess game, but there's a lot of ways you can go and a lot of branches, and Minimax just can't search it very well because there's too many branches. So if you preloaded it with a bunch of information about chess grandmasters and how they usually open their games, that would save it a whole lot of computation later, right? So you can hard code things that are known about the game. The disappointing thing about that from an AI perspective is that's not general at all, right? That's very chess specific. And yeah, in fact, a really good chess AI is going to have all the chess specific stuff crammed into it that it can. Basically, I'm disinterested in that because I'm only interested in general purpose stuff. So let's talk about any general purpose improvements. What do you think we could do next? Multi-thread, so that's a good one. You know how Moore's law is kind of dying? We're basically saying, okay, well, we can't do smaller transistors anymore, so we're branching out into parallel processors. Everybody's machine now has 8 cores, right? I mean, your phone probably has 4 cores on it. So you can make it 4 times faster simply by multi-threading. You can, and it's only going to increase in the future. If you can get it on the GPU, you've got hundreds of parallel processors that can do things. Can you parallel process a recursive algorithm? Yeah, you got to do stuff, but you could make it not recursive, and that's just fine. So remember, it doesn't have to be a recursive algorithm. It just has to explore a tree. And recursion is just one really easy way of implementing that. So we've got all these branches we can prune. What do you suppose would encourage pruning to occur frequently? You know how we prune in the condition of when the node finds something that's so good that the node knows that the other player can see it too, and would therefore never choose it as an option. That's when we prune a branch. We don't just prune a branch, we prune the remainder of all possible moves, right? What's the branching factor in chess? The average branching factor in chess is about 35. What that means is at any point in a game, you have about 35 possible moves to choose from, right? Well, look at this picture. What's the average branching factor here? 2.5-ish, 2 maybe. This isn't very representative. Imagine if there were 35 children to every single node. When you encounter this condition of alpha-beta pruning, you're not just pruning a branch, you're saying, stop looking at any children. Don't even bother exploring any more of the remaining 30 children of node 4, because, I shouldn't call it node 4, that's not a unique number, but it would stop looking at all the children because it knows that its parent would never choose it because it's already too good. How does an AI know that it's okay to make a sacrifice to get something better? What has to happen is you have to look deep enough. If your tree goes deep enough, then you might sacrifice the knight right here and take a queen right there. Or you might sacrifice a queen right here and win the game right there. If you look deep enough, then the AI will make all those kinds of sacrificial moves. The time when it doesn't is if the payoff is farther into the future than your tree goes deep. So part of the name of the game to making a brilliant AI is it has to look infinitely deep. And of course you can't look infinitely deep, so the more processing you do, the deeper you can go, the better the AI will be. How many moves do professional players and grandmasters think ahead? I think the answer is no one knows because they don't really look, like they'll look some number of moves ahead, but there's no way they're going to exhaustively look ahead. And so I think what humans do is we're very good at discerning when you go ahead in this branch, that's just a dumb branch. I'm not even going to explore that. Whereas a computer explores every possible move. And I think that difference that's a lot of the difference between AI and a human. When I'm sitting there playing someone, I can probably do 2, maybe 3. I mean, my strategies aren't that intricate. And I know I'm not seeing everything because when I play a AI that's looking 3 moves ahead, it's hard for me. So maybe you're better than me. Great, I don't care. But I think you'll find your chess AI with 5 move look ahead, I bet you it beats every one of you. Am I right? Anybody able to beat your AI at even 4 look ahead moves? How can we get this thing to look farther ahead? Here's the trick. Because we prune all of the remaining children, alpha-beta pruning makes a huge difference to chess. It prunes as soon as we've found a pretty good move, right? Once the move is pretty good, then this node knows, hey, I'm pretty good. Therefore, my opponent won't allow that to happen. Therefore, the sooner you can find a good move, the sooner you can prune everything, and that ends up being pretty much the name of the game in writing a powerful chess AI. The commercial ones will make a big deal about sorting your possible moves. So I wrote this move iterator that iterates over all possible moves, and it's just arbitrary. If you wanted to make a really good one, here's what you do. You'd find your set of moves, and then you'd go and you'd think to yourself, well, hey, moving these pieces are more likely to yield good results, and you'd probably do some lookup tables. And you might look one branch ahead to kind of get a hint on what's going to happen. And if it's a move that kills something, hey, that's probably a good move, right? So if you could peek ahead and find out whether it kills something, then you could order the moves and sort them and know whether or not to do the full recursive search on that branch. And that way you're much more likely to prune. Turns out that increasing your chances of pruning makes your code a whole lot more efficient, so you can search a lot deeper and therefore make a more powerful AI. Has anybody ever heard of iterative deepening? Imagine if you say, look ahead 3 moves, and so you go ahead only 3 moves down your tree, and then you look ahead 4 moves, and then you do it again looking all the way down 4 moves, and then you say, okay, do it again, now looking down 5 moves. How much does that cost? That's going to be more expensive, right? Because you're repeating work you've done before. Well, surprisingly, a lot of students don't realize this, it doesn't cost as much as you'd think. So consider a tree. Let's just do a binary tree because they're easy to reason about. So if you have a binary tree of depth 1, it has the number of nodes is 1. With a depth of 2, the number of nodes is 3. With a depth of 3, the number of nodes is 7. With a depth of 4, the number of nodes is what? 15? And then 31, and then 63. You see the pattern? It's always powers of 2 minus 1. Right? So let's say we're off by 1 and just call this powers of 2. Suppose this were 2, 4, 8, 16, 32, 64. And I know I'm off by 1 here, but pretend these are the depths, the sizes of the tree, right? Okay, well, 1 plus 2 is going to be a 3. Okay, 1 plus 2 plus 4 is going to be a 7. 1 plus 2 plus 4 plus 8 is going to be a 15. 1 plus 2 plus 4 plus 8 plus 16 is going to be 31. 1 plus 2 plus 4 plus 8 plus 16 plus 32 is going to be 63. Okay, the point I'm trying to make here is this. Even if you iteratively repeat, you do the depth of 1, then the depth of 2, then the depth of 3, then the depth of 4, in the end you're doing only twice as much work as you would do anyway. So if the cost of looking through your whole tree is order n, then the cost of iteratively going deeper and deeper until you reach the depth you want is order n. Technically it's order 2n, which is the same as n from a perspective of computational complexity. Do you see that? So this is amortized computation. And I've also done that with a branching factor of 2. What happens if you have a branching factor of, say, 35? Instead of order n, it's going to be order 1.002n or something like that. So it makes a less of an impact when you have a larger branching factor. And that number I just stated was totally pulled out of nowhere and exaggerated. So it isn't 1.002n, but it's less than 2 is what I'm getting at. Here's another way to measure it. If you run your code with a depth of 3 and then you run it again with a depth of 4, it's a lot slower, right? And if you run it with a depth of 5, all of a sudden it's unbearably slow. So much so that if you added to it the cost of doing a depth of 4, it's almost negligible. Haven't you found that in your implementations? Okay, so what I'm saying is you can do iterative deepening and it doesn't cost much. What's the advantage of that? Why would you maybe want to do iterative deepening? Every time you go down a little farther, you get more information, right? If we search down a depth of 3 this way and we haven't killed anything yet, do you see how we're just kind of probably exploring dumbness? Whereas if we were searching down this way and we got the opponent's queen, you're almost certain that's a good path. So you might as well go deeper down that branch. And so you can actually go deeper down the branches that are productive and less deep down the branches that are not productive. Moreover, every time you get to a branch, you can sort the moves by how good you're expecting them to be. And if you can sort them, that increases the likelihood of pruning, which means you can search a whole lot more of your tree with less computation. Then of course the other thing we can do to make this better is just throw bigger iron at it, right? If you have a modern computer with fast processors, you can just search really big and deep. Is anybody familiar with the whole Kasparov versus Deep Blue debacle? No? Okay. Well, that's just kind of an interesting part of AI history, so maybe we'll mention that. Deep Blue was built by IBM, and it was this machine that was supposed to be amazingly intelligent because IBM has a big hype machine and they love trying to show off how intelligent their systems are. Well, they challenged a world chess grandmaster who at the time was Garry Kasparov, or Kasparov, I don't know how you pronounce that, and they decided to play chess against each other. And they played a whole bunch of games, and first match was actually won by the human. So this is kind of the modern John Henry, right? Man versus machine, see who's finally going to win. Kasparov was doing well, started beating the machine. Turns out that later in the game, Deep Blue started winning and ultimately prevailed over Kasparov. Well, then a controversy came out. It turns out that the IBM team was in the background tuning the machine and making adjustments to their AI while the game was playing. So Kasparov claims that he wasn't actually beaten by a machine, he was beaten by a whole team of humans who were actually messing with the AI. And quite arguably that's a good claim because it wasn't a clean room laboratory fair type setting. So for a long time people were claiming that machines have never truly beat humans. Well, Deep Blue of course comes back and says, well, this time we'll play it fair and we'll set it right. So they kept challenging chess grandmasters, but of course they all refused because they claimed IBM was playing dirty. And to this day, there are still people out there who claim that machines have never beat humans at chess, at least not the really, really, really good ones. Basically, nobody who knows anything about it would really defend that claim because we all know that since 1996, processing power has gotten way, way better, right? And we can search orders of magnitude deeper, and the truth is if you play a modern machine in chess, it will beat the pants off of you. The reason why we're having trouble proving that machines can beat humans at chess is really because the humans are taking their ball and going home. Truth is, AI has long since surpassed humans at chess, but there is a little bit of controversy out there about it, and it's kind of funny. There was a joke, if you poke around on YouTube, you might find ads about this. There was one called Deep Blue versus Kasparov, the rematch. And this one was at a swimming pool. And the idea was that here's Kasparov in a Speedo, or some actor representing him, sitting on the platform where you're about to jump into the pool. And on the other platform next to it was a big machine. Somebody fires the gun, the machine falls into the water, sparks fly, it dies, Kasparov swims across the pool and wins. The whole point is, hey, even though machines may be better at humans at very, very ultra-specific tasks, humans generalize, and that says a lot, doesn't it? I mean, we can solve a whole range of problems, so even though we have AI, we don't really have general AI yet, right? Yet. There's another one where they're doing basketball, and Kasparov is dribbling the ball around this machine that's just standing there in the middle of the court, computing, or doing what computers do. And it's basically emphasizing that, hey, this is stupid. Machines just can't do what humans do. Yet.